Welcome to another coding tutorial, and in today's video I'm going to show you how to create this dynamic Truchet tiles with matter.js. This is part 2 of a 3-part series. In the previous video, we have already created some hexagonal tiles and the 4 patterns A, B, C, and D, and we also added some sound to make it a pretty cool sketch. In this video, we're going to add some physics into it using the library matter.js. It's basically my take on this piece by Ruben Medellin, which actually is an inspiration for this whole series. And then in the next and the final video, we're going to be adding some interactivity with the p5.js library, or the machine learning library. There are a lot of moving parts in this tutorial, and it took me a while to wrap my head around everything. So first, let's go through a few math concepts, starting with this one, where I'll show you how we'll approach the pipe geometry by turning the thin strokes into solid geometry that matter.js can collide with. As you can see from the 4 patterns here, there are 2 types of strokes, a straight line and an arc. For a straight line segment, the pipe is created from 2 rectangles placed an equal distance on either side of the line. Let's look at just one rectangle. We need to calculate both the direction and the distance from the line segment, connecting point 1 and point 2. To calculate the direction, we first find the direction between the 2 points by doing vector subtraction. You can either do p1 minus p2 or p2 minus p1, but you just need to be consistent. For now, I'm going to do p2 minus p1, which means the direction we get is where p1 is pointing towards p2. Then we normalize the vector, or shrink it to the magnitude of 1, and then rotate it by 90 degrees. This gives us the perpendicular direction to the line segment. Next, to calculate the distance, we need to know how far the pipe sits from the line and also how wide the pipe is. Knowing the direction and the distance, we then place 2 points around each endpoints, one pair at the outer edge and the other pair at the inner edge. Then we connect those 4 points in order to get one thin rectangle, and then we repeat it for the opposite side. As for the arc segment, it is the same idea. The pipe comes from 2 offset arcs on either side of the middle arc. But instead of just calculating 4 points like the straight pipe, we sample many points along 2 curves, an outer arc and the inner arc. We start with what we already have, which is the arc center, the radius of the middle arc, and then the angle range, which we'll call starting angle and the ending angle. And we already calculated this in the previous video. To calculate the distance, or the radii, for the outer edge and the inner edge, we need to know how far the pipe sits from the middle arc and also how wide the pipe is. After that, we can figure out the points along the edges using trigonometry. X equals to r times cosine of angle, and y equals to r times sine of angle. For the outer arc, the angle starts from starting angle to ending angle, while for the inner arc, the angle starts from ending angle to starting angle. And we want it this way because we need to stitch all of these points together to create one closed polygon. And then we do the same for the other arc. Instead of starting from scratch, we're going to start from a sketch that is based on what we did in the previous video, but I have modified a few things. First, I have changed the variable names from r to be hex r, which is the hexagon radius, and I've created a new variable called arc d, or arc diameter, and I set it equal to hex r. They're the same value, but this way it's a bit more readable. And I have reduced everything into just one hexagon, so let me just click run to show you what it looks like. And then now when you press 1, you can rotate the hexagon. Okay, so let's go to hex.js file here. What we want to do, also inside draw a pattern here, there's only one pattern, which is pattern A, and then we'll put the other patterns back once we understand how to create a pipe. So how about I comment out these 2 line of codes first. So we have this one line here. So let's start by creating just one pipe. What I'm gonna do is actually, instead of writing the methods inside this class, I'm actually gonna come down all the way here, and I'm going to write utility functions. So these are going to be the functions that we can reuse to create these pipes. So let me just write utility functions. The first function that I'm going to write is going to be called getRect. And it is going to have a total of 4 parameters, right? So 0.1, 0.2, and then distance from center and the thickness. So the thing that we want to do first is we want to find a direction between the 2 points. So let me create this variable called dir for direction, and it is going to be a subtraction, vector subtraction between the 2 points. So p5.vector.sub, and because I want it to be p2 minus p1, so I want it to be the direction that points from point 1 to point 2, and in my case, point 1 is going to be the bottom one. So we're going to put in p2, comma p1. And then after that, what I want to do is I want to normalize it. So we can just do dir.normalize. This basically just makes this vector to have a magnitude of 1. And then I want to find the perpendicular direction to this direction, right? So what we want to do is, how about I create another vector called perp, P-E-R-P, and then I'm going to first copy the direction vector. Then I'm going to rotate it by 90 degrees. So that is half pi. So it's going to be rotated clockwise. So let's say that the line, the direction is pointing from downward here to upward here. So if I rotate it clockwise, it should be pointing this way to the right. And once I have the perpendicular direction, what I want now is that I want to figure out the distance of the outer edge and the inner edge. So how about I create 2 variables, let's call them outer edge. This one will be perpendicular. So I'm going to copy this vector and I'm going to multiply it by the distance, right? And the distance for the outer edge will be this from center plus thickness divided by 2. And the inner edge will be very similar. So I can just copy this, but instead of plus here, it will be minus. And now we have what? Both the direction and the distance. What we need to do now is we need to calculate those 4 points that will make up this rectangular shape. So I'm going to call the point, let's do P2 outer, which is going to be this point. It's going to be p5.vector.add, and we're basically adding what? Adding p2 to outer edge, right? And then I'm going to do this one next, which is going to be p1 outer, which is p5.vector.add, and it's going to be p1 comma outer edge. And then we're going to do the inner edge for p1 next. And the reason that I'm doing it in this order is because they need to actually there needs to be points that make up this rectangle, right? So that the points are all create this closed polygon. So it's going to be p1 comma inner edge, and then lastly p2 inner, which is going to be p5.vector.add p2 inner edge. And then we want to return all of these points in this order. This has to be P, P2, P10, P1I, P2I. Okay, so let's just check to see if this function works. So I'm gonna come to draw patterns here. How about we create a variable called points, and then let's just do get rect, and the first 2 points are going to be midpoints 1 and 4, right? So 1 is the bottom here and 4 is the top there. So okay, and how about we first set the distance. So let's go back to Sketch, and here, how about down here? Let's do distant from center. I'm actually going to set it relative to the radius of the hexagon here, divided by 6, and then we'll do the thickness to be 8. And you can play around with these variables later. Okay, let's go back to here. Okay, so this will be what? This from center, and then thickness. So before we start drawing anything, why don't we just print them out just to see what's in here? Looks like I had a typo here, so oh, I thought I fixed it. Okay, so I have a vector. I have an array with 4 vectors, and these has 2 x and y location, right? So that's right, we have the 4 points that creates the rectangle. So now why don't we just draw them out? So for let I equals to 0, I less than points, I points dot length, I plus plus, and then how about we draw them as vertex? So vertex points, so points of I dot x, and then points of I dot y. And to use the function vertex, we also need 2 additional functions, begin shape and end shape, to actually be able to see these vertex points. And I want to also add an argument close, but I'll just show you without. Oh, you can still see it. It doesn't close completely, but because we have this hexagon, you can see that it's close. But if I put in close here, it just makes sure that the polygon is closed. All the 4 points, the last point and the first point, are connected. Now I also want to change the stroke weight to be a little bit thinner. So thick. Okay, let's go back to 1. All right, so now that we have the pipe on the right, let's do the same thing for the left side. So I'm actually going to write another function. How about we call it function get rect pair, and essentially we need the same exact parameters here, and we're going to do let left pair to be equals to get rect of this, right? So on the left side, it has to be negative distance from center, but on the right side, it still is what we have here, which is the positive right pair. And then we just return left pair and right pair. Now in here, if I do pair, right, we give it the same arguments here. If I click run, it no longer works, even if I do pair like this, because it's a 2D array basically. So what we need is that we need to write another for loop. So let I equals to 0, I less than pair dot length, I plus plus, and then actually inside here, this will be pair of I dot length, right? And we change this to j. Ooh, this has to be I of j, then pair of I and j. Okay, I hope that is not too confusing. Basically, we have the exact same thing, but we have 2 pairs, the right pair and then the left pair. So we need to go through each rectangle first before we can draw the shapes. Let's try it. Yay! Okay, so now we have a working pipe for the straight segment. Now let's try the arc. All right, so for the arc, I'm going to write more utility functions. So let's start with just one arc. So I'm going to call it get arc. But for get arc, we're going to need a little bit more arguments. So what do we need? So as we went through it previously, we need the center. So let's do cx and cy. We need the middle arc, or this arc here, radius, and then we need the distance from center. Basically, actually, distance from center is a little bit misleading, but I'm going to use that so that it's consistent with this variable here. This is the distance from, I guess it's from center. It's from the center arc. So it's the distance from this arc. And then thickness. Then we also need starting angle and ending angle. And we need the step, right? Because we need more than just 4 points. So in here, what we need now is, how about we calculate the radius that we want first. So r is going to be center r plus dist from center. Yes. So we'll just do the distance that we want, and then we can do the outer radius, which is going to be r plus thickness divided by 2, and then our inner will be r minus thickness divided by 2, right? And then this will get us the pipe. Now we just need to loop through the angle. So let's do for let I equals to, let's do let a equals to 0, a less than the starting angle. So because we're going to do the outer arc first, a plus plus, we also want to declare an array for the outer points, and then an array for the inner points. So here we also want to create a conditional statement to make sure that the points are within the arc. So current angle, and this is the angle as we loop through this. So we'll say if a is more than or equals to, this is if a equals to start angle, and if it's less than end angle, right? Then if a is greater or equals to end angle, then let's set current a to be equals to an angle. We don't want it to be bigger than that. And then else, current a should just be a, which is whatever it is in the loop. Then after we have this, then we use trigonometry to find the points. So let x equals to r, for the outer it should be ro times cosine of current a, and then y to be ro times sine of current a. But don't forget to actually also move it by cx and cy, right? Because everything is relative to this point here. And once we have this, now we just want to add these points to the outer array. And I'm going to create an object by using this syntax here. So a curly bracket, and then we're going to set x to be equals to this x value here, and then y to be equals to this y value here. All right, now we're going to do a very similar thing for the inner arc. When I say inner arc, it might be a bit confusing. So because this arc here, there is this inner pipe and this outer pipe. What I'm talking about here, we're just working with just one pipe, but in that one slice of a pipe, there's the outer and the inner side, right? So now we're gonna work with the inner side. So for let But now it has to be A equals to n angle. If A is greater than start angle, then we subtract it, right? Because we need to do it this way so that all the points are all line up to create one closed polygon. So let current A, if A is less than or equals to start angle, then current A will be equals to start angle. Else current A equals to A. Then I'm going to just copy this. But then we're going to change this to RI, and then this is the inner array, right? Now we have the points inside the outer array and then the points inside the inner array, and we're going to combine all of these inside an array called combined points. Very creative, I know. But I'm doing this in like a very kind of maybe not the most efficient way, just to help you see the big picture, but you can refactor it later. So I'm going to create another variable. Let's call it let combined points. We start with an empty array. Then we're going to loop through the outer array. And then we're going to add all these points into the combined points array. We're going to do it the same thing for the inner points, the points inside the inner array. Combined points dot push inner of I. Then now we have all the points inside the combined points array. All we need to do is we need to return combined points. Okay. And for safety checks, what we're going to also add is two conditional statements. The first one is if step is undefined, I want to make sure that it is set at pi over 24. And this increment, you can set it the way that you want. So this dictates how many points there will be inside your array. And then the second one is if starting angle is actually greater than an angle, which it should not be, then we're going to add one loop, one revolution of a circle, which is 2 pi, to an angle, just to make sure that the an angle is greater than start angle. Okay, that was a lot of coding. Let's give it a try. So inside here, what we're going to do is first going to do the same thing. So I'm going to create a variable called points, and I'm going to set it to get arc. And let's see, what are the arguments that we need here? So we need cx and cy, which for this arc, it is these two things. Center R. Center R is the arc diameter divided by 2. Distance from center is distance from center, and thickness is thickness. Starting angle and an angle. We also have this. And then step. Let's just not put anything in for step. And it should work because we have that safety check right with undefined. Let's try it. Oh, actually I don't want to delete that. I'm going to print points out first. Also save. Okay. There should be more than 6 points, I think. Did I do something wrong? pi over 24. Actually, why don't we try and draw it out too? For let I equal 0, I less than points, dot length, I plus plus. Then let's do, actually I'm going to draw with an ellipse. Points of I dot x, points of I dot y, size 10. Location seems right, but the amount doesn't seem right.
A few moments later.
Very weird, because I put in step there, but there is no step. I guess it assumes step to be something else. Alright, so this looks correct. Look at that. Okay, so instead of having an ellipse, we're going to also use the function vertex. Then do begin shape and in shape close. All right, and we're going to do a very similar thing by creating another function called getArcPair. So down here, I'm going to do function getArcPair, and it is basically going to take the same parameters here as well. Down here. All right, and we're gonna have two variables, outer arc and inner arc, right? So outer arc will be getArc. So outer will be this from center like this. Ooh, and then inner will be the opposite, right? So inner arc will be negative this from center. And then we just want to return outer arc and inner arc. And in here, same thing, right? So this will become pair, get arc. Let's do arc pair, get arc, and now we'll get two pairs, inner and outer. So basically we also need a nested for loop, right? So let I equals to 0, I less than arc pair dot length, I plus plus. Then we're gonna add this inside here, and this will be arc pair of I dot length, and then this will be arc pair of I and j, and this has to be j. Arc pair of I and j. Run. Oh, I didn't change this to get arc pair. All right, this should work. Alrighty. Okay, so now we get an arc pipe, two pipes, a pipe, two arc slices. So now let's do the same thing for this third side, this side. So how about we just copy and paste this down here. Let's change the number to 2. And then we also need to change the cx and cy, right? So this will be this dot corners of 3, and then we also need to change the starting and the ending angle. Okay, I think that should work. Nice. And as I press 1, now it rotates. Perfect. So before we move on to the other patterns, I'm going to refactor the code so that it's easier to read and also preparing us for the later part where we start adding matter.js. And what I really mean by that is that, as you can see here, basically these functions provide us with vertex points, and we're using them here inside draw patterns, but that's not actually what I want to do. I want to create a separate method that basically keep all of these points so that we can use that to create the matter.js body later, and then inside this array or whatever it is, then we'll be drawing points from there. Okay, so what we're going to do is we're going to create an array. Let's call it this dot polygons. And then we're going to write a new method. So maybe we can write here. So how about we call it get polygon bodies. And I'm going to also put this here, this dot get polygon bodies. We basically want to call it in the constructor function so that we get all of these points inside this array, this dot polygons, right when we create one of these hexagon object. So inside here, I'm actually also going to write another method called add pair, which will be taking in a pair of something. So basically a pair of these shapes, right? So instead of doing this in a nested for loop, I separated them. So inside here, what we're going to do is that I'm going to loop through a pair, which basically has two, right? So pair dot length I++, then inside that this polygons array, I'm going to push whatever is inside this pair. So pair of I, and basically we also need to know what this pair is, and it is going to be whatever is returned from these functions, right? So that is, we're going to use this as a helper function to get the polygon bodies here. So for pattern A, which is the pattern that we're working with right now, what we need to do is we need to add pair, and we need to add a total of 3 pairs, right? So what we're adding for the first one is we're adding the first pair, which is this. I'm gonna put it inside here. Then the second pair is this arc here. And then the third pair is this second arc here. Okay, and as you can see, we have this small arc length defined here. So I will also copy and paste this inside here. Okay, so when we call get polygon bodies, now this dot polygons array is populated. And what we want to do is now we can basically delete all of this. I'm also actually going to delete the middle lines also. So now if I click run, all the lines are gone, but don't worry. Now we have the polygons, right? So we're just gonna loop through this dot polygons dot length I++. Before we do that, actually, I'm going to print this dot polygons dot length to show you now that there are a total of 6, right? Because we have the straight line and then the 2 arcs, and each of them has 2 polygons associated with them. And now out of the 6, then what we can do is we can draw the points out. So no, we need a nested loop, just like before. Let j equals to 0, j less than this dot polygons of I, j plus plus, right? Because out of the 6, they have their own vertex points. So vertex of this dot polygons of I and j dot x, this dot polygons of I and j dot y, and then don't forget begin shape and end shape. Close. Run. Ooh. I think yes, forgot this is dot length. Yay! Okay. Still rotates. Now we can put in all the other 3 patterns. So we're gonna put them inside here. So it's gonna be switch this dot type, then if case A, then we do all of this. Okay, and then I'm gonna go and do the other cases.
A few moments later.
Okay, let's try the other cases if it works. B. Okay, do you see that? There are some rounding errors here that makes the shape not completely an arc because it doesn't reach the end here. So what we can do very easily is inside the get arc function here, we just add a tiny bit of number here, and then the same thing here. Oh, this has to be negative. And now it's fixed. Right, so let's try the other shapes. So A, B, C, and D. Alright, so this video is already kind of long. So if you want to stop here and then come back later, you can. But if you are strong enough, let's get moving and we're going to start the matter.js part. I know you're strong. Alright, let's get going. So if you have no idea what matter.js is, it is a physics library that I actually love to play around with, and I have quite a number of tutorials on the library already. So if this is your first time, I recommend watching some of the basic tutorials before. But I'm actually going to walk through the basic with you a little bit right now, so you can just watch here and then see how much you can follow. First, what we're going to do is that we're going to come to this arrow here, and then we're going to go to index.html, and what we're going to do is that we're going to actually add the CDN location of the library. So I have here matter.js version 0.20.0, and as you can see here, I have an additional package called poly decomposition, and this is going to help us when we create more complex shapes. It's basically help us decompose complex shapes, and for us it's like the arcs that are in the concave shapes into convex shapes. But basically this package is going to make our life easier. First, I'm going to extract objects from the matter.js library. So let's do const and then this curly bracket, and we're going to add engine bodies and composite. We're going to set it equals to matter. This is called object destructuring, and it allows us to, instead of having to write matter.something or like matter.engine, matter.body, we can just now call engine, body, bodies, and composite alone. And then I'm going to declare a variable called engine. Inside setup, I'm going to create this engine, this physics engine. So to do that, basically we just do engine equals to engine dot create. And then inside draw, because I'm using p5 as the renderer, we're going to be updating the engine this way. So engine dot update, and then we're going to put engine inside here. Click run, and now we have created the physics engine, but we don't see anything yet. So why don't we create a box? And I'm going to call it new box. And I'm actually going to go to their documentation page right here from matter.js, and then let's go to bodies. The matter.bodies module contains factory methods for creating rigid body models with commonly used body configurations. For example, rectangles, circles, and other polygons. Basically, when we call bodies dot something, circle, rectangle, polygons, it basically creates an object that has all the properties that we need, that we want for that particular shape. And the shape that we want to create for now is actually a rectangle. And we need x, y, width, and height. Okay. So new box. So in here, we're gonna do new box equals to bodies. You saw before it said matter.bodies, right? But because we did object the restructuring, we just do bodies, and then dot rectangle, and we need x, y, width, and height. So I'm actually going to declare x equals to 100, y equals to 100, and then let's do box size to be equals to, how about 30. So we have x, y, box size, and box size. Then once we create the new box here, we also need to add it into the world, the physics world that we created inside this engine. To do that, we do composite.add. The world is actually a composite, but it's the top level composite. And we're adding new box. And no, the first argument actually is going to be where we're adding it to. So we're adding it to the world, and then we're adding what? We're adding new box. And inside draw here, I click run. You don't see anything because we have not rendered this box. Basically, we need to draw it out. But I want to actually print out new box.position just to show you that it exists already. And you can see that the y position keeps increasing, right? Because it's falling down based on the physics that is being acted upon this box. So now what we're going to do is we're going to just draw out the box using the rex function inside p5. And we're going to do new box.position.x, new box.position.y, and I'm actually not sure how to extract the width and the height from this, but because we have the same box size here, I'm just going to put in box size. And click run. And I also happen to know that the orientation of the box inside matter.js has the anchor point at the middle of the box itself. But right now, our box is being anchored at the top left corner. So we're gonna also change the rec mode to center. And what I'm gonna do also is I'm going to write a function, mouse pressed, and instead of just creating this rectangular box, just one box here, we're gonna create new boxes every time that we press the mouse. So we can just copy or cut this 2 lines of code, and we're going to create a new box every time when we press the mouse at mouse X and mouse Y location, and we're going to add it to the world. But also we want to create an array, let's call it boxes, and So this is separate, right? This is adding the box into the world. But to draw it out, we're adding it to the boxes array, which then P5 can see, and then we will be drawing these boxes out inside the draw function. So boxes.push new box. And now here we need to write a for loop that loops through the box array, and we're going to be drawing out the rectangle at boxes of I, run. Click, 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 click. Did you see it like hit each other a little bit? But you can't really see the effect of the physics library, except for it's falling without us having to actually write our own gravity. But I'll show you in a little bit. Before we get there, let's actually create a class. So let's come to this arrow here, click create file. Let's create a rectangular rect class inside this rect.js, and make sure that you add this file into index.html file here first. So let's do rect.js. All right, so let's go back to rect.js here. I'm going to create a class called rect, and inside the constructor function, what we need is we need these. Actually, just need this. Okay, and I'm actually going to call this as this.body, and we're going to create 4 parameters: x, y, width, and height, the same way that the matter.js rectangle method asks for, right? And I'm going to set this.w to width and then this.h to height, because we actually cannot, I don't know how to extract these 2 values from the matter.js object itself. And then here, mouse x, mouse y will be x and y, and box size will be this.width and then this.height. We're going to be adding this new body into the composite or the world. And then how about we write the display method? And the display method basically is just this, right? Drawing the rectangle at this.body, this.body, this.width, this.height. And now let's just do every time we press the mouse, new box is going to be a new rect object at mouse x, mouse y, width and height, which is box size, box size, and then here it will be boxes of I.display, right? Because inside this is the box, the rect object. All right. Before we move forward, also, I want to write 2 additional methods. One is called check done, and the other one is called remove box. So if you're familiar with some of my tutorials before, basically we want to remove all the boxes from the boxes array when they move off the screen. But I have an additional method here called remove box, because we also want to remove it from the world. So it is very similar to this line of code here. We just do composite.remove, and we're just removing from the world this body. And then check done, we basically want to check if this dot body dot position dot y minus this dot height. So the top of the box is greater than height. Then let's do this dot done equals to true, else this dot done is equals to false, and then we're gonna set this dot done to be false initially. Now inside Sketch, what we want to do is first we want to check done, and then we want to say if boxes of I dot done is true, then we want to do two things, right? We want to first remove it from the world. So we just do boxes of I dot remove box. We actually want to do this before we do this next thing, which is removing it from the boxes array. Because if you do that first, then it's already gone from the array, so we cannot remove from the box. We cannot call this. Basically, this I is gone. So we're using the function splice, providing in the argument that we want to remove it, and then the number of object that we want to remove from that index. So just one, so that particular box. And to do this, we also want to loop it backwards as to not to skip any of the objects inside the array. So we're gonna do I equals to boxes of dot length minus 1. If I is greater or equals to 0, then we subtract it. Okay. And how about I print out boxes dot length just to see that this works. All right. And then now I want to show you how to create a static matter.js object. So actually I'm going to create ground. And ground is going to have XY location and also width and height. And X and Y location will be width divided by 2. I want it to be at the center. The X and Y location of a rectangular matter.js object is in the middle, right? So it's going to be width divided by 2. Height, how about we do height minus 100, and then width will be the same width of the canvas, and then height, let's do 10, and then ground will just be bodies dot rectangle of gx, gy, gw, and gh. But this time we can also create, as you can see here, options, right? So this options here actually is just, there are a few options I think, but the one that we're going to use is called isStatic. So if it is static, if isStatic is true, that means that this box doesn't move. There's no physics, there's no gravity, just like the boxes that you saw that kept falling. Then now I'm going to draw the ground. So rect at g, x, g, y, g, w, and then g, h. Oh. What did I forget? I forgot to add it into our world. So composite.add engine.world ground. Ta-da! Okay, perfect. So when we create the pipes into the matter.js body, we also want isStatic to be true. Now, the last thing I want to do before we put everything together is also that you can see that right now the box does not rotate, but it can actually rotate. So what we can do is first inside display here, instead of drawing everything based on this position, I'm going to use some translation function. So translate, we want to translate it by, let's call x to be equals to this, and then y, and this will now be 0, 0. I'm basically translating the origin, and then we need to make sure that we put push and pop so that it saves the transformation and then it returns it back to the default location before it calls the next box. So right now nothing changes, and then what we want to do is we also can put this outside here, set angle to be this.body.angle, and then we can put rotate by angle. And you see, it rotates. So now I'm going to combine this sketch with the original sketch.
A few moments later.
All right, so now I have the hexagon, and then I have these boxes that are way too big. So let's make it 10, but now they don't do anything, right? So what we want to do is essentially making these pipes, right? These wall pipes here to be matter.js static objects. How are we going to do that? So we're actually going to be using this matters.bodies.from vertices. X, Y vertex sets are what we need to calculate basically. Let's see here. To optionally enable automatic concave vertices decomposition, the polydecomp package must be first installed and provided. So this is exactly what I said earlier. We already pretty much integrated it onto the sketch already, so we're good. The resulting vertices are reorientated about their center of mass and offset such that body.position corresponds to this point. So right now we have all the vertex points, and these vertex points are actually relative to the center of the hexagon. So what we need to do is that we need to do some conversion. I'm actually going to be creating another utility function called centroid, and we're going to provide all the list of points, and then we're going to be able to find center of mass, and then we're going to subtract it. And then next, we need to find this x and y location. To find this x and y location, which is the location of the centroid, this is relative to the canvas. Now we know where the centroids are, right? After we do the calculation, we need to know where it is relative to this dot post, which is where each of the hexagon lives. And we already have this dot post, so now we just need to know the relative distance and also angle. For the distance, we can use the built-in function dist to find the distance between these 2 points. And in terms of the angle, we can do the inverse tangent equation to find the relative angle between the 2 points. Then we're going to add that angle, that new angle, from between the center of the hexagon and the centroid. And then we add it to the actual angle of the hexagon as it moves, right? Which is the current angle. And that will be the new angle. And then once we have the new angle and then the distance, we just add it to this dot post, and then we'll find the actual x and y coordinate of the centroid that should live on the canvas. All right, I hope that is not too confusing, but we'll go through the code together in a little bit. Inside this class here, we're going to first calculate the centroid, right? So we're going to find 6 centroids of the 6 polygons that makes up these pipes. And I'm actually first going to create a utility function called centroid. And I'm actually not going to go through how this function is written right now. It is based on the shoelace formula to find this center of mass based on the vertex points. So you can, I'll link up some of the useful notes on this formula, and then you can go and take a look. All right, and basically this function returns x and y coordinate of the centroid, right? And you just need to provide polygon, and polygon basically is an array with sets of vertex points, which we already have. Let's go back up here. Okay, so we're going to declare bodies. This is going to be an array that keeps all of the matter.js bodies. And then I'm going to loop through this .polygons array here, right? And there are a total of 6. What we're going to do is that we're going to find the centroid, set it equals to the function centroid, and then provide this .polygons of I, right? Because each of the objects, right, has its own vertex points, and we find the centroid. Then we also want to create an array called centroid, and we're going to add the center of mass, the centroid, inside this array here, and then we're going to create a body. We're going to call it this.body. No, let's do let.body equals to a new function that I'm about to write, a new method. Let's call it make matter body, and this is going to take in this dot polygons of I and also the center of mass, and then we're going to push it inside this dot body array. Okay, that was a lot. Was that a lot? Let's keep going. We're almost there. Right, we're going to write make matter body method that takes in polygon and centroid. First, we're going to convert the vertex points relative to the centroid. Actually, instead of calling this polygons, I'm gonna call it polygon verts, so that it's not confusing, so that you know these are vertex points. I don't know if that's easier to understand, but let's keep it. So we're gonna call this vertex set. Yeah, it's an array. We want to go through all of the points inside polygon verts, right? The name. Okay. GHANGHT length. Yeah. I++. And then we're going to subtract it from the centroid, right? So polygon verts dot x minus centroid dot x. Y is the same thing, so polygon verts of I dot y. And then we're going to push it inside this new vertex sets. And this is basically the points that we're gonna provide in as the third argument of the bodies.fromVertices function inside the matter.js body, right? Okay, so once we convert this, now this is convert relative to centroid. Then next we need to find centroid location on the canvas map, right? So as I said before, we need to find everything relative to the center of the hexagon first. So we're going to find the distance, let's call that r, the distance between the center, which right now we'll just set it to be 0, 0, first, and then we'll add everything to this dot pose, right? So 0, 0, and then it will be centroid of x, centroid of y. Then we need the angle also, so let's call this alpha, inverse tan, and we use inverse tan too so that it helps us with the orientation, which quadrant it is in, so it can output the right sign. Yeah. So we want centroid of y and then centroid of x as the second argument. And then the new angle. So now everything is relative to, first there's the angle that this hexagon is rotating, right? And then there is the angle alpha here, which is the angle relative to the center from the centroid. So new angle will be this dot current angle plus alpha. So we have these three. Now we want Rx. So right now it's just the two, the hexagon center and the centroid. So it will be R times cosine of new angle. And then Ry is R times sine of new angle. And we're not done yet, right? Because we actually, at the end of the day, we want the location of the centroid on the canvas coordinates. So we need to do canvas x to be equals to this dot pose dot x plus Rx, and then canvas y be this dot pose dot y plus Ry. All right, so we already have the vertex sets of all of the vertex points that is with the centroid as the local point 0, 0. And then we have the location canvas x and canvas y, which is the location of the centroid on the canvas map. Now we're ready to make the bodies. So let body equals to bodies of from vertices canvas x, canvas y, and then vertex sets, and option is going to be is static will be equals to true. And I think we need to put in true for the fifth argument too, and I think that's what the decomposition needs for us to be able to call it. I think, yeah, I know that if we put true here it works. All right, and then don't forget to add it to the world, right? So engine.world add body. And I also want to set the angle of each of these new body that we created, and we can do that using body.set angle. So we want to set the angle, how much the new bodies here is rotated, right? And it is going to depend on this dot current angle. So this dot current angle, which is the angle of the hexagon here. And then we're going to return body. All right. So this method here is going to be called here, right? And then it's going to be pushed inside here every time that we start creating this hexagon shape. So I'm going to save, and then I'm going to run. And then I got I less than and the set body here, you don't just put the angle, you need to give it also which body to rotate. So it's the body here. All right. Oh, you see that? It kind of worked, but as I rotate here, it doesn't work, and that is because we made it work, but we only call make matter body where inside the constructor function, so it never updated. The all of these needs to be updated, but we don't need to create the body over and over again. So what I'm gonna do is actually basically we need to calculate this again every time inside update. And inside update here, say for let I equals 0, I less than this dot polygons dot length I plus plus. So we have these, but we don't want to create a new body, right? But we want to set the angle, and we want to set the new position also. So where did it go? Here. So yeah, we want to set angle like this, and then body dot set position. We want, okay, so actually this, it's not just body anymore because that was part of a function. So now here it has to be this dot bodies of I, right? Because we already created that. Same thing for here. And then X and Y, it will be X is going to be the canvas X here, and then Y will be canvas Y. And then all of these centroids here are the centroids that we already calculated. So centroids of I, this dot centroids of I. Okay, you might need to rewatch this video a few times, but I hope you understand how everything is put together. I think this is correct. All right, let's give it a try. Boop, 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 boop. Rotate. Oh! I think this is it, guys. Oh my God. This is a face of happiness. Okay, all right. Almost done. So next what I'm gonna do is that I'm gonna put this inside a grid. So I'm gonna bring back all the columns and everything. And yeah, let's do that.
A few moments later.
All right, so let's see what I did here. Basically just brought back all of the calculations that we did in the previous videos to make a grid, right? And then here created a bunch of hexagons that has random types. And then down here, basically just make a nested loop to call update and display. But now this no longer works. Actually, I'm going to delete this and also bring back the random method that we used in the previous tutorial. So it's rotating randomly. And actually, how about I make it a little bit smaller, and then I'm going to make the box sizes smaller too. Oh, actually, let's keep it 10. This feels good. All right, so now I just want to do the last thing, just make it pretty, and then we're going to be done. I promise we're going to be done. So let's go back to Hex real quick. And I want to add this .c, the color, to be a random color inside the palette that we have created. And I want to make the stroke weight to be 2. And yeah, oh, no. The color here actually is going to be part of the rectangle here. And display, let's do no stroke. And then we're gonna do fill, oops, this .c. Guys, we did it. We really did it. Oh my God. Okay, I'm gonna go eat lunch. All right, I really hope that you enjoyed this one. It was so fun for me to figure this out, honestly. I haven't done a tutorial that actually tickle my brain this much in a long time. So I hope that you enjoy it and give it a try. I think this puts together a bunch of different concepts, different libraries. And yeah, stay tuned to the next video where I'm going to add a little bit more using the p5.js library to make it even more interactive. I hope that you try this one. Bye!